Hello, good afternoon, everybody. Welcome to the Coastal Modeling Systems Advanced Topics webinar, day 3. Thanks for attending. I'd like to ask everybody if the audio is okay, if you can hear me. Good. I apologize for cutting off yesterday early. We had a power surge here, and the internet went out for several minutes. We didn't know how long it was going to last, so we decided to stop the webinar and continue today. So apologize for that. Okay, so let's go ahead and get started with the webinar. Today, so yesterday we finished the initial and boundary conditions. Well, actually, we finished the boundary conditions. I'd like to go over the initial conditions today, and then after that, talk about the surface roller, salinity transport, and then sediment transport. Just as a reminder, the webinar material is under the Tech Transfer tab of the Coastal Inlets Research Program website. There's a section for this week's webinar, and you can download the workshop material there. The link is provided here. I posted today a new version of the CMS user's manual. Actually, well, this date is not correct. I didn't update this figure, but if you go to the website, the wiki, it has the date of today, the 20th. I added a few sections. I'm sorry about that. I added a few sections and made some corrections. So please download the latest version of that. Okay. And this is what the new version looks like. So going to hydrodynamics and boundary conditions. Yesterday we left off, I believe here, with the water surface elevation boundary condition. We didn't talk about tidal or harmonic boundary condition. Before I get started with today's topic, is there any questions on yesterday's webinar? By the way, feel free to send questions at any time. I won't be checking the questions until I reach the end of a section, but you can submit the questions at any time. So I'll try to cover little pieces of the webinar and then pause to read the questions and then answer them if they haven't been answered already by the organizers. Several of the attendees sent us some emails yesterday with questions, and they were all very good, and I'm happy you did that. I really encourage you to do that, to send us emails. If you have a complicated question and you'd rather talk about it, feel free to do that too. We do that all the time. Okay. Okay, so now tidal and harmonic boundary conditions. This is a water level boundary condition. The difference between tidal and harmonic boundary conditions is that the tidal one includes nodal corrections and equilibrium arguments. So this is the general formula used to calculate the tidal boundary condition. And as you can see, it has A is the amplitude and F is a node factor. So A is the amplitude of the tide for each constituent. F is a node factor that varies with time, and it's a correction to the mean amplitude. So when NOAA, for example, calculates the amplitude of a specific constituent, let's say M2, they do it over an epoch, a tidal epoch of 18.6 years, something like that. And that's an average. But actually, the amplitude varies in time, and that node factor is intended to account for that. Okay. Omega is the tidal frequency, T is time, and then these two numbers are what's called the equilibrium phase. And they account for temporal variations in the constituent phase lag. Okay, and both the node arguments and the equilibrium argument are only applied when you apply a tidal boundary condition. Okay, when you apply a harmonic boundary condition, it's assumed that it's just an idealized case, and maybe your reference time is not meaningful. It's just a hypothetical case, so it doesn't apply those correction factors. Is this clear to everybody? Okay. The tidal constituents that are available in CMS are listed in table 2-3, and there's 37 of them. Only a few. Well, actually, I do remember talking about this yesterday. I covered it briefly, but I'll cover it again today. These are the constituents included that are available in CMS. SMS only supports 8 or 9, but you can go into the CM cards file and enter any of these. We talked about the cross-shore boundary condition. And the other topic is the initial condition. The initial condition in CMS is there's two types, a cold start and a hot start. And to see more about that, you can go to Chapter 4, hot start. Okay, so the default initial condition for CMS is a cold start, and that means that all of the variables, current velocities, water elevations, concentrations, everything is set to 0. So you have 0 energy, basically it's cold. The second option is to do what we call a hot start, and when you specify a hot start, you need an initial conditions file. And you can make that file yourself if you have a known initial condition, which rarely you do unless it's an idealized case, or if you have, well, maybe you have the results from another model that you can use to generate the initial conditions file. And how to do that is described in this section. Okay, it tells you what the variable names are that need to be stored in that file and the path where they need to be stored. Basically, the data that goes into the initial conditions file goes into an XMDF file, and so it's a hierarchical format, and the variables are like in a hierarchical tree, and this is the path and the name of the variables within that file. It talks about how to create the initial conditions file, and it's very simple to do in the interface. If you have, for example, results from another model, you can interpolate those onto your CMS flow grid and then export them into that initial conditions file, like it explains here. So in this example, you can see that the user created these data sets, water surface elevation and velocity, that he sampled from a solution file, and then you simply export them into an XMDF file, and that's it. When you go to the CMS flow model control window, you check the box and then you specify the name of that initial conditions file. Now, the hot start file is the file that CMS writes while it's running, so you can restart from that time later in case the simulation crashes or the power goes out, or in our case your computer is shut down for updates by IT. So it's also an XMDF file, and there's two options for writing it out. You can write it at a recurring interval, and that's really what we recommend. But you can also specify a specific time to write out that file in the interface, and that's shown here. As far as concentrations and sediment transport, you can specify the initial condition for sediment concentrations and also salinity in the same file. Otherwise, they're assumed to be 0 at the start time. One important thing to note is that when you are hot starting a simulation, it's important to set the ramp time to 0, right? Because you don't want to affect your model forcing or boundary conditions. Okay, so that's how the initial condition is handled in CMS. Is there any questions on the initial condition? Okay, there's a question by Matt asking if I can talk about how to specify boundary conditions from another model or using nested grids. Sure. If we go to Chapter 4, hydrodynamics, and then boundary conditions. This is actually this section here called creating and deleting cell strings. I added in this new version of the user's manual. And this is what I was talking about yesterday about the, just a second, about examples of good cell strings and bad cell strings. This is on the right-hand side, you see a good cell string for a flux boundary and a bad cell string for a flux boundary. And on the left-hand side, you see kind of like an ocean or cross-shore cell string. And the one on the bottom is bad because not all the cells are at the boundary, and also the cell string doesn't reach the end of the boundary. Let me go to answer Matt's question about the extracting boundary conditions. Okay. So there's a section called extracted water levels. When you want to extract boundary conditions, you can do two things. You can in the interface, you can select the water surface elevation forcing and either define a curve or extract from a regional model or use tidal constituents. If you select a regional model, then you need to have loaded in SMS a larger grid of another model, either AdCirc or CMS Flow, and then you would extract boundary conditions from that solution, from that grid. The other thing you can do is select water surface elevation and velocity forcing, and also extract from a larger solution, model solution. And so here you would pick water surface elevation and then current velocities, and then you say extract. It's important to keep in mind the time settings here that you extract for the right time period. This is the way we do it now. Honestly, I don't like it very much because we do sometimes long simulations of about a year. And if you extract boundary conditions for a whole year, it takes a long time in SMS. And so this summer, we're developing utility to extract boundary conditions more automatically. So where you can specify a solution file sample that spatially and save a CMS file that CMS could use to extract boundary conditions on the fly, interpolate that spatially and temporally. That's the way we're going. If you give me a second, I can load an example of a nested grid for Shark River Inlet and show you all the steps. So in the workshop material that we've provided, there is a folder called, sorry about that, boundary conditions, and inside of that there's a folder called nested. And this has the two options, the option where you specify only water surface elevation and the option where you specify both water surface elevation and velocities. So just going to this one. So as you can see, this is a small subset of the larger CMS flow grid. Sorry. I'm going to go ahead and load that, the larger grid, which maybe I'll just use this one. So the way it works is that you would run the larger solution, the larger grid, for whatever time period, and then you'd load it with the solution file in SMS, and then you go to the smaller grid, the nested one, select its cell strings, say apply boundary condition, and then you can extract from the regional model. See? So here you select water surface elevation, because I selected only water surface elevation in the boundary condition window, and say extract. I'm not going to do it here because it's already done. And I don't know if the time periods match or anything. Or you could say both water surface elevation and velocity, and you do the same thing. You say extract, select the water elevation, and if there's several vector data sets, it'll give you the option to pick one of them, but usually it finds the right one. And again, say extract. Once you've done that, you can save your CMS flow. Oh, this reminds me, I talked about this the other day, is I never save the project files, the SMS project files. I prefer saving each component separately, saving CMS flow by itself, saving CMS wave by itself, and saving another, saving the map module stuff separately. I prefer doing it that way, but some people in our group like saving the project file with everything. I just don't like the naming convention that it uses, where it appends the project name in front of every file name. That's really annoying to me. I hope that answers your question about how to nest CMS flow within another grid. Does that answer your question, Matt? Is there something you would like for me to cover with that? Something I'm missing? If not, then I'm going to move on. And again, the user manual covers in detail how to do this step by step. Yesterday we covered pre-processing time series. We covered the initial conditions. So at this point, if there's no more questions, I'm going to start talking about the surface roller. Okay. So the surface roller model is kind of a separate model within the CMS. You have CMS wave, CMS flow, and the surface roller is kind of a separate model. It works on the CMS wave grid, but it's kind of weird because you control it from the card file, the CMS flow card file. And it's the surface roller basically refers to the part of the breaking of the wave that is is the aerated region of the wave. So when a wave breaks, you get all this foam and bubbles and turbulence, and that kind of travels with the wave, and that's the roller. So what happens is the momentum of that wave goes into all this turbulence and that foam, and then later it goes into the flow. So there's a lag that's produced in the momentum transfer between the waves and into the flow. Okay, and this is how we account for that process, by taking the energy from the wave model, which is the wave breaking energy, transferring it to a roller model, and then from there into the flow model. Okay, and what it does is it causes a spatial lag between the spatial lag in the peak alongshore current. It moves it closer to the shore, and that's seen in the field, and without the surface roller model you cannot reproduce that. It also has the effect of kind of smoothing the wave forcing, and so it improves stability a lot. And if you look at our VNV reports that we published last year, including the surface roller makes a huge difference in the near-shore hydrodynamics, and it improves the results significantly. The only I guess bad thing about the surface roller is that it really is empirical, and it has these empirical parameters that vary a lot. Okay, and we have default values for them. The parameters I'm talking about are the roller dissipation coefficient, which varies between about 0.05 and 1, and also this efficiency factor, FE, which by default is 1, but can also vary between 0.5 and 1. And for more discussion on how the surface roller affects the results and how to modify those parameters, you can refer to the VNV reports that we published last year. By default, the surface roller model is not turned on in CMS. You have to turn it on. And like I mentioned, it runs on the CMS wave grid. It's also a steady-state model, as you can see, and it runs every time the CMS wave model runs. It runs right after that, before CMS flow starts. And I'll go into the steering procedure in a second. So by steering, I mean how the CMS flow and CMS wave are coupled. Is there any questions on the surface roller? So again, the default setting in CMS is for the roller to be off, and the reason for that is because this option is not yet in the interface. We don't want we want to be backward consistent with previous versions of CMS where it wasn't there. When it becomes part of the interface, then we will change the default for it to be always on, but at least the user will be able to see it when he or she is setting up the model. If there's no more questions on the surface roller, then I'll move on to salinity transport. CMS calculates the depth average salinity conservation equation. It's not appropriate for every kind of application. It's only applicable for well-mixed places where you don't have stratification. And the interface is pretty simple for that. I believe Mitch covered most of that last week. You just basically turn it on, specify time step, and the only other parameter you need to specify in the model control is the initial condition. And that is given as a spatially varying data set or a constant. And at every cell string in the model domain, you need to also give a time series for the salinity, and it's constant for that whole cell string. I don't think I want to spend too much time in salinity. Really, it's not the. I see there's more questions. I'm gonna. Okay. There's a question that says, should the roller mass flux be turned on if the surface roller is on? And that's a very good question. That goes back to the wave mass flux. Okay, in Chapter 2, section wave mass flux velocity, we define the wave mass flux velocity as this equation here. And as you can see, it has two components. E sub W is the part due to Stokes drift, and E sub SR is the part due to the surface roller. If you turn on the surface roller, then you are able to turn on the roller mass flux, but you don't necessarily have to have it there. The reason why we do that is because for some field applications, you get better results if you don't include the roller mass flux. Okay, and this has to do with the depth averaged approximation, because we're using because it's a 2D model, I should say, not depth averaged. Because it's a 2D model, where there's no vertical variation in the current velocities, and if that leads to error in, how can I explain this? It turns out that for some cases, not including this is better for some field cases, and the reason for that is because of the 2D approximation. If we were using a quasi 3D or 3D model, then it wouldn't be so. So I guess the answer to that question is it doesn't have to be on if you turn on the surface roller. By default, it is not on. So you want to modify that in the card file. And let me show you what the cards look like. Okay, so this is one example where I turned on the surface roller. In this case, I was not using the wave average formulation. I just turned on the surface roller, and then I gave the roller dissipation coefficient and the roller efficiency coefficient. This roller scheme refers to the transport scheme, and the options are a first order upwind scheme, a second order upwind scheme, and the Lax-Bendroff scheme. And those options are described in Chapter 4, section I think it's missing the bookmark for it. Looks like I don't have that part. That's a good catch. So I just realized now that the CMS User's Manual is missing the section to describe the cards for the surface roller. Fortunately, the workshop material has an example of that, how to specify the cards. I'll add that this afternoon and then post an update to the User's Manual. It's only those cards that are in that example, these 4 cards, and the roller mass flux. Okay. Yes, the numerical methods for the surface roller is described in Chapter 3, surface roller. So this is what I was talking about, the first order upwind scheme, second order upwind scheme, the lax Van der Waals scheme is not described here because I don't like it, so don't use it. And this is how it reaches a steady state solution by doing a time stepping procedure. Okay, and the roller model is very, very fast. It's pretty stable, and so including it in the CMS simulations is really recommended. It doesn't take much time or to calculate. Let me see if there's any questions. Okay. Let me go back to salinity transport. Well, salinity transport is very basic in CMS, and I think that's all I'm going to cover for that. I really want to get into sediment transport because I know that's going to lead to a lot of questions, and I need to spend more time on that. Probably going to have to continue with sediment transport tomorrow. Okay. CMS has the option to simulate. It has 3 sediment transport models. An equilibrium total load model, an equilibrium bed load plus suspended load model, and this one, a total load transport model. This model, in the implicit code, it's the only one that is supported, and the explicit solution scheme supports all 3. Okay, so that's important to keep in mind. And when you're in the interface, this is what I mean by that. So if you select the implicit solution scheme, then you're allowed to choose the non-equilibrium sediment transport model, total load non-equilibrium sediment transport model. Now, the wording in the interface is not the greatest, really, but we're changing that for the next SMS interface. If you select the explicit scheme, then you can select the total load non-equilibrium model here, or you can choose advection diffusion. And what that means is the equilibrium bed load plus AD equation for suspended load. And then total load, this refers to the Exner equation. Okay, those 2 options are only available with the explicit solution scheme at the moment. There's a couple of reasons for that. First of all, the total load model is I would say kind of the antiquated model. It's not used very more in literature because it assumes equilibrium transport everywhere, and that's really not realistic. Advection diffusion, which is non-equilibrium for suspended load plus equilibrium bed load, is more common to see in the literature, but it still assumes equilibrium load for bed load, equilibrium transport for bed load, which is less of a stretch than for suspended load, but still it's not as realistic as non-equilibrium transport. And so when you select the implicit scheme, it's saying that it's giving me errors about the time step. This is annoying. When you select the implicit scheme, solution scheme, you can only use the non-equilibrium total load model. Okay, and that's the model that's described in the user manual here. Non-equilibrium total load transport model. And this model is a multiple size sediment transport model, but you can run it as a single size sediment transport model also. So there's kind of like 2 modes of the model. This is the transport equation. It has a temporal term, advection term, a diffusion term, and you can see that it only includes the diffusion of the suspended load because the diffusion of bed load is assumed to be relatively small. People usually don't include it, although some people do. Some like ADH, for example. And then this term here is a source and sink term, And we use the adaptation concept for the source and sink term, which says that the erosion and deposition is proportional to the difference of the concentration capacity and the actual local concentration. And as you can see, C has subscript TK, which means for total load, which stands for total load, and K is the fraction, is the size class. And size class, what we define as size class is that when you have a range of sediments, you need to discretize that range into individual size classes with a characteristic diameter and also limits. Okay, but let me show you a grain size distribution to make that more clear. If you go to Chapter 4, Sediment Transport, Multiple Size Sediment Transport, no, actually the figure I'm looking for is in Appendix E, determining the size classes. So this is an example of a log normal grain size distribution, which is common for coastal sediments. And each bin is a size class, and it has its limits, diameter limits, and also it's characterized by a characteristic diameter. Sorry about that. And we calculate that the characteristic diameter in CMS like this, using the geometric mean. Okay, but now, before I get into all of that, I want to keep describing the theory for the sediment transport. I want to go back to Chapter 2, the non-equilibrium total load transport model. Okay. So beta sub Tk is a total load correction factor which accounts for the hysteresis effects. Basically, those are temporal lags between the flow and the sediment transport, and it is due to basically the non-uniform distribution of the current velocity profile and the sediment concentration profile. And we described how that's calculated in a subsequent section. There's hyperlinks in the document that you can click on to take you to that section. R sub Sk is the fraction of suspended sediment for each size class. Okay. One important parameter in the sediment transport model is the adaptation coefficient. As I mentioned, we use the adaptation concept for calculating the erosion and deposition at each cell. And I've heard some people call this a relaxation approach, but it's really not a relaxation approach. Numerically, it looks like that, but it has physical meaning. And some people have derived analytical expressions for the adaptation coefficient. This section is way too detailed for me to describe it during the webinar, but I encourage you to read it. And there's lots of options in CMS, many options for the adaptation coefficient. And what I recommend that you start with when you start a project is to use a constant total load adaptation length. That's the simplest method, and let me show you how you do that in the interface. Go to sediment, turn on sediment transport. The total load adaptation length can be calculated as a constant. You can use the maximum of the bed it's suspended. You can use a weighted average of them. I always start with just a constant, okay, and then modify that to get an idea of how sensitive my results are to that parameter. If I realize that the results are not sensitive to that parameter, then I'll just leave it. If I realize it is sensitive, then I'll go I'll do more tests and try different options. I'll set up a script to set up multiple cases, maybe 10, 15 cases, and then try them all for short, simulate short periods of time. how sensitive your results are to the adaptation coefficient depends on your problem. It depends on the size of the problem, and how big your grid cells are compared to that adaptation length, and how dynamic your problem is. Okay? Let me go back here to the user manual. If you have a very small, tiny inlet like Shark River Inlet that's dynamic, and your grid cells are 5 meters, then probably your results are going to be sensitive to adaptation length, because your adaptation length is on the order or larger than your grid size. But if you have a project in a place like Galveston Bay or Grace Harbor or Chesapeake Bay, really large areas where your grid size is going to be 30, 40, 50 meters, your adaptation length is smaller than your grid size, and therefore changes in your adaptation length are not going to affect your results that much, because basically what happens in the model is that your equilibrium reaches your sediment reaches equilibrium from one cell to the other. If that makes sense, if I'm able. Yes, the adaptation length is related to the distance it takes for the sediment to go from non-equilibrium to equilibrium. And if your cell size is larger than that, then every time the sediment moves from one cell to the other, it's already in equilibrium. I hope that makes sense to everybody. If there's any questions on the adaptation length, I'll take them now. I know it's a complicated topic. So for example, in the V&V report, for the laboratory cases that we ran, some of those were sensitive to the adaptation length, but they were laboratory cases, very small scale, high resolution cases. When we do field cases of large places like Grace Harbor, Columbia River, the results are not sensitive to the adaptation length. They are a lot more sensitive to the equilibrium sediment transport formula for every case. Okay, for small scale, large scale, that really most of the error in sediment transport comes from, let me show you where it is in the equation, comes from this guy here. And that's not just for CMS, that's for every sediment transport model. Equations that we use to calculate the potential sediment transport rates or capacity are what introduce the most error into the model. Okay, because that's really the driving force of the model. It's going to say where you have sediment transport and how much you have of it moving. And so when you run sediment transport with any model, I encourage you to test different equilibrium sediment transport formula. In the case of a 3D model, then you have equations that give you the near bed concentrations. Most typically uses the Van Ryn formula, for example, for coastal applications. If there's no more questions on the adaptation coefficient, I'll move on. So we have lots of options for calculating it. Some people use the adaptation time. For example, XSpeech uses the adaptation time, and you can either specify constant or they have a very basic, simple formula to estimate it. And the adaptation coefficient is still really a topic of research. I talked a little bit about the total load correction factor, which accounts for the vertical variations of the suspended load, the bed load, and the current velocity. And this is how it's defined. And we have two options for calculating it, assuming a log distribution of the current velocity profile and either a exponential profile or Rouse profile for the concentration profile, for the sediment concentration. And in these figures, you can see how it varies as a function of these non-dimensional parameters, the Rouse number and this phi parameter. And what we do inside the code is you don't want to calculate those nasty integrals every time step. So we save a lookup table that's basically this figure here, and then we interpolate each time step. Another parameter that we need, or variable that we need in the model, is this bed load velocity. And we use a formula by Van Ryn that was recalibrated by Wu. And it was really developed for the case of currents only, but it's commonly applied to the case with currents and waves. How valid that is, or how accurate, I should say, that is, really don't know. There's no formula out there that we can find, that I've seen, that will give you the bed load velocity under combined currents and waves. So that's an area for research. So the transport equation moves the sediment. Okay, transports it by advection and diffusion. The equation that calculates the bed change is given by equation 2.5-51, and it has basically the same source term as the transport equation, plus another term that accounts for the effect of the bed slope on the bed load. So when the bed is sloped, the sediment will, because it's bed load, it's hopping, it's rolling, it's sliding, it will tend to go down slope, and that's parameterized through this diffusion term that has a bed slope coefficient d sub s. That d sub s varies between 0.1 and about 1. The default in SMS, I believe, is 1, but I like using a number of about 0.1. P sub n prime is the bed porosity, and in CMS we assume that the bed porosity is constant, as well as the sediment density. F sub morph is a morphologic acceleration factor. This is what other folks, like the Dell folks, they call the Morphac factor. And it's intended to speed up the simulation or speed up the bed change. We don't use it very much, but in literature you'll find people use numbers like on the order of 100, but we don't like to do that. The model is fast enough that we can simulate it in real time, and that way you don't need to worry about additional error introduced by this morphologic acceleration factor. It's really only valid when you have periodic conditions, when you have forcing, and that's cyclical. Okay. Otherwise, it's not realistic at all. Okay. And because it's a multiple size sediment transport model, we calculate the bed change due to each grain size class, and we sum those up to get the total bed change. And the bed is discretized into vertical. Well, I see there's some questions. Let me take those now. Okay, Alan Zundel is asking if d sub s is a vector quantity. No, it is not. The d sub s, which is the bed slope coefficient, is a scalar, and it's constant for the whole domain and the whole simulation and time. It could be quantity and try to estimate it as a function of the grain size and different, maybe the bed slope, different parameters. But really, there's just not enough evidence to be able to estimate a formula for it. Right now, we just use a constant. We wish we could estimate it, but really there's no equation for it. It's available in literature. It's a topic for research. Another question is, what F-morphs values have you used for projects? By Allison. We we don't use the morphic factor, the morphologic acceleration factor for projects that often. We have used values of about 20 to about 10 to 20. Any larger than that, then I wouldn't recommend with CMS. We've tried using values of about 50 or 100, and the model just gives really unrealistic results compared to the case where you set it to 1. So I don't recommend using values larger than 20 if you have to use it, but really the CMS is fast enough where you don't have to use it. And then there's another question: how do you account for transport from upslope? Transport from upslope. I'm not really sure what that question is referring to, from upslope. Is the question referring to avalanching? Alan, can you okay, all right. So this term here, which accounts for the effect of the bed slope on the bed load, causes the sediment to move downslope. Okay, the bed slope doesn't cause the sediment to move upslope. Okay, the transport upslope is an advective process, and that's included in the transport equation. In this equation here. So this equation allows sediment to move upslope by advection and diffusion. And this term, if I can find that equation again, is a correction to the transport equation for the bed slope. I hope that makes sense for everybody. Does this answer your question, Alan? Okay, I'm looking through the questions, and okay, so on we go. One alternative approach to this is to include this term in the transport equation. And we tried that at the beginning, and we just found that this approach gives better results. You know, how to explain that, I can't say, but it just does. So on to bed material sorting and layering. The bed, when you use the model as a multiple site sediment transport, the bed is discretized into vertical layers. The top layer is called, or we call it the mixing layer. Some people call it the active layer, and it's the layer of sediment that that's being actively exchanged with the sediment transport. The second layer and the third layers and below are buried layers. The second layer does exchange sediment with the first layer if that boundary moves up and down, but the third layer does not exchange with the second layer. and the equations that we use to calculate the bed sorting. By bed sorting, we mean is the change in bed composition of each size class in each layer. Okay, so we have a grain size distribution, and for each size class we store in the model the fraction of that size class in the bed, so that the sum of all the fractions is 1. Okay. And figure 2-5 shows a schematic of how the bed layering evolves over time. Just an idealized case where you have an initial bed, the top layers, the colors just indicate the layer number. The top layer is the mixing or active layer, and then so forth. There's, I believe, 10 layers in this example. And as the simulation goes on, time goes on, it erodes the bed, and it gets to a point you can see here where that second layer is too thin. You can only have a minimum thickness for each layer, and when it becomes too thin, it's merged with the layer below. And then when the layer becomes too thick, like in this case here, it is split into 2, and that's how the algorithm works. So when 2 layers are merged, a layer is added at the bottom. When 2 layers are split at the top, 2 layers are merged at the bottom, and that's how the algorithm works. Is this clear to everybody how the model uses size classes and the concept of the bed sorting and gradation in the model? I find that some people have a hard time understanding this. They don't understand why the size classes are constant for the whole domain. Now's the time to ask about this before we move on. All right. So there's lots of ways of estimating the mixing layer thickness. As a minimum, it is twice the median grain size, and also half the bed form height. But we also take into account the deposition of the during that time step. Something very important in the model, like I mentioned before, is the equilibrium concentration and transport rate. The equilibrium fractional sediment transport concentration is given by CTK star, and CTK, let me highlight these numbers. So this number is the potential equilibrium total load concentration. This is how much you would have, how much concentration you would have for a size class if there were no other size classes involved, basically. But because you only have a fraction of that size class in your total transport, then your fractional equilibrium total load concentration capacity is given by this one here. And all these definitions are a mouthful. Apologize for that, but it's just the way it is. The depth average equilibrium concentration, the way we define it, is with this equation here, 2-58. And this is a very important definition because not everybody defines the depth average concentrations this way. Some people define it by just taking a simple vertical average of the concentration without including the current velocity in it. For example, let's go back to the non-equilibrium total load, the section that talks about the total load correction factor. Our definition of the depth average concentration is this. sorry about that, I'm still learning how to use this software, is this equation here divided by the depth average concentration. So as you can see, the depth average concentration as defined in CMS is weighted by the current velocity, and not everybody defines it this way. This definition is more convenient for a depth average model because it simplifies the transport equation and the calculation of other parameters. That's why we use it. For example, when it allows us to use this simple equation. Okay, there's lots of formulas in literature to estimate equilibrium transport rates, and if we want, and we can take those equations, those empirical formula, and directly calculate the number that we need, the concentration capacity, by simply dividing it by the volume flux. Okay, U times H. This is why we do it this way. People that don't define the concentration this way, I'm sorry to take so much time on this, but I think it's important, especially if you want to compare the model concentrations to data, field data. People that don't define the concentration that way include correction factors in the advection and diffusion terms. Okay, that's how you can tell by just looking at their transport equation what definition they are using, by whether they have correction factors in the advection and diffusion terms or not. Okay, going back to the equilibrium transport formulas. We have several formulas available in CMS. The default is the Lundstrup sediment transport formula, and these were developed within our group since maybe 2004, 2005, and they work pretty well. They calculate separately the bed load and suspended load, and they were developed originally for single-site sediment transport. That's why you see D50 here and not D sub K. Now we have taken them and applied them to multiple grain sizes. I'm not going to go over all the details of the user manual. I'm just going to talk a little bit about how we've modified them for multiple site sediment transport. And last year we published we did some research on this and validated extended the Lundstrup formula for multiple grain sizes using this approach here, where we include a correction for hiding and exposure, which is this parameter here, and another correction for with the sediment availability, so how much of that size class is on the bed. All right. Another option for the transport formula is the Van Ryn equations, the simplified equations, the ones that he calls the one-line model. And those are given by equations 2.2-86 and 2-87. Again, they were developed for single-size sediment transport, and we have extended them to multiple-size sediment transport in a similar way to the Lundstrup equations, except the hiding and exposure, in this case, is applied to the critical velocity, which is more appropriate for the form of the equations. Okay. In the case of Lundstrup equations, because of the form of the equations, we couldn't do it that way. But in this case, we can, so we did it that way. The other option, this is supposed to be Van Ryn equilibrium transport formula, and that's given by 2-92. And we have also extended that one to multiple grain sizes. And then Watanabe. Watanabe is there for kind of backward compatibility and historical reasons. It's not really the most accurate formula, but it's useful for comparing with. Okay, now I mentioned hiding and exposure a little bit. Before I go into that, let me look at answer some questions. Okay, the question is the hiding and exposure, the availability of the bed applied to all the transport formulas or just the Lundstrup? And the answer is yes, they are applied to all of them. And in the manual we describe how they are applied to each formula. depending on the formula, it's a little different. For example, there's also these scaling factors for bed and suspended load, this F sub B and F sub S. In the case of, for example, the Soulsby-Van Ryn formula, they're applied to the coefficients, these coefficients, that give the amount of bed load and suspended load, okay? Because there's not a separate formula for bed load and a separate one for total load. It's kind of combined into one. Now, this parameter here is the heighting and exposure, and similar to the Van Ryn formula, it's applied to the critical velocity. And this is the most physically accurate approach, and it's also done with the Van Ryn formula. As far as the sediment availability, that in all the formulas, it's just a directly multiplied by the formula. It's included in the front of it, like you see here. And that's the standard practice. Most people do it that way. Okay, so how is the heighting and exposure correction factor calculated? Or what is it first? When you have multiple grain sizes, what happens is the larger grains tend to shelter the smaller grains from the flow, and also kind of keep them from going up into suspension. As you can imagine, they're trapping them. And that's what we call the hiding effect. So the larger grains hide the smaller ones. But at the same time, the bigger grains are more exposed to the flow because they're kind of sticking out from the bed, and that's what we call exposure. And this process is accounted for by just a simple correction function that we include in the transport formula, as I mentioned earlier. And the way it's applied depends on the formula, and also there's empirical coefficients that are associated with this parameter that vary for each formula. And I'll go into that in a second. As I mentioned in the beginning of the sediment transport, it is possible to run CMS as a single-site sediment transport model. So if you do that, what that means is that you're only transporting one size class, okay? Because you need to solve a transport equation for each size class. Now, it's possible to do a heighting and exposure correction even if you have a single size class, by assuming that the bed composition is different from the size class that you're moving. And if you do that, then it's possible to calculate a heighting and exposure correction function like this, equation 2-101. And you have this empirical coefficient m, which varies between about 0.5 and 1, depending on the transport formula and site-specific characteristics. As you can see, it's only a function of d sub k, which is the transport grain size, and d50, which is the bed composition, the local bed composition. Okay, and because it's a single size sediment transport model, the d50 does not change. This is a kind of an ad hoc way of including an important process in a single-size sediment transport model. And we did this early on when we didn't have multiple grain sizes. This is the option that is available with the explicit model, which currently does not support multiple grain sizes. A more realistic approach, but also computationally intensive approach, is to use multiple grain sizes. Okay, and if you use multiple grain sizes, then the heighting and exposure correction factor is calculated using this function here, where P sub EK and P sub HK are the total hidden and exposed probabilities calculated using 2-103. I'm sorry if this webinar isn't visually stimulating, visually interesting. That was the feedback that my wife gave me the first day. She said that the webinar was visually boring. Sorry about that, but you know, when you talk about equations in theory, that's how it is. So Allison has a question. Will a single D50 model simulation run a lot faster than a simulation with a set of sediment size classes? And the answer is yes, definitely. If you run multiple grain sizes, you might have 5, 7, 9 size classes. And what that means is you need to solve 5, 7, 9 transport equations and bed sorting equations and bed change equations and store all the bed layering and do those calculations too. There's a lot more computations that are involved with that. It's probably it's orders of magnitude more computationally intensive. But because the equations are linear, they're you know, compared to hydrodynamics, say, it's not as computationally intensive as hydrodynamics, but still it is. So when setting up a project, you know, the preliminary runs, the test runs, I would recommend setting them up with a single size sediment transport model, and then once you've got that working, you can add complexity to the problem by including multiple grain sizes. Is there any questions before I move on with this? Okay. The horizontal sediment mixing coefficient is equal to the turbulent eddy viscosity divided by the Schmidt number. And the Schmidt number has a default value of 1, but it's user adjustable. Boundary conditions for sediment transport. Inflow boundary conditions are defined by an equilibrium concentration. Outflow, the model just allows the sediment to flow out. It applies a 0 gradient boundary condition for outflow conditions. It is possible if you have a river at a location where you know the sediment flux and you want to specify that as a boundary condition. It is possible to do that in CMS, but you have to do it right now, at least, with the advanced cards. And so you can either specify a total sediment transport rate given by this, or you can specify a fractional sediment transport rate at the boundary. And the transport is distributed across the boundary according to this formulation here. This equation, I'm sorry. Normally we don't have to do this because we rarely have field data. And the equilibrium assumption is pretty good one. Also, when you specify a sediment flux boundary like this, it can cause problems if it doesn't match very well with your empirical equilibrium transport formula inside the model domain. For example, your data says that you have so many thousand kilograms of sediment coming in, but your equilibrium formula says it's only 20. Well, all that sediment is going to come into your domain and just fall out, and it's going to create a big mound right at the boundary. And so it tends to cause instability problems. That's why it's not used very much. I've only used these for flume cases where it was measured accurately, and I can apply it with confidence. And we already covered the salinity transport. what I'd like to go into now is how to set up the multiple size sediment transport now that you know all the theory behind it. Is there any questions on the theory before I move on? Okay, so if we go to chapter 4, section sediment transport, this is how the interface for CMS 11 looks like. And it describes all the basic cards for that. Now, there's some advanced things that you can do. For example, specify the fall velocities for each size class if they were measured. I don't recommend that you use fall velocities for calibrating the model. That's not standard and it's not recommended. But you can also specify what formula you want the model to use to calculate the fall velocity. And by default, it's the Solvay-Whitehouse formula. But you can also use a Wun-Wang formula, which I like because it includes the shape of the particles, how round or jagged they are, and the calculation of the fall velocities. As I mentioned earlier, the porosity of the bed is assumed to be constant through the whole simulation. And table 4-25 gives some typical values for different beds as a function of how sorted the sediments are and how well packed they are. So the porosity can vary between 0.46 and 0.3. Again, you don't want to use this for calibrating the model. It's not going to affect your results that much. I've seen people try to calibrate the results to the porosity, and you can spend days on that. It's not going to affect your results that much. We talked about the sediment transport formula. These are the cards that are used this is the transport model. These are the cards to specify what transport model is being solved. And then the sediment transport formula, the 4 options, the Lundserp, Van Ryn, Watanabe, and Soulsby Van Ryn, and all the associated cards with those. Scale factors, the bed and suspended load scale factors. These are the factors that directly multiply by the equilibrium transport formula. And these are calibration parameters, and they are the most important calibration parameters. Well, one of the most important, I should say. They typically have values between 0.5 and 2, but if you look at the literature, the papers that propose those equilibrium formula, transport formula, they compare with lab data, and the scatters within a factor of 5, and that's for lab data. For field conditions, you're extrapolating those formulas, so you expect the error to even increase. Using a value between 0.1 and even 10 is not unreasonable for field applications. These numbers are spatially constant at the moment, and they are used for, the same number is used for all of the size classes. I think that later we would like to change this, because once we're adding, in the process of adding cohesive sediment transport. And when you do that, by necessity, we have to use different formula for different size classes. And so applying a different scaling factor for different size classes makes sense then, okay? Right now, not so much. Morphologic acceleration factor, that's the card that you use to specify that. And then I mentioned the Schmidt number earlier. Adaptation length, there's a lot of stuff for that. I see there's some questions. Let me go ahead and take those now. Oh, okay. There's a very good question that says, when can we assume that we have a multiple size, I guess, problem? And one good number to look at is the sorting. There's what people call the sorting coefficient, but you can also use like a standard deviation. If you go to chapter 4, section multiple size sediment transport, and you scroll down, here we define there's a couple of definitions for the geometric standard deviation. there's a graphical method, and then there's a geometric method for defining the standard deviation, sediment standard deviation. And those are given by equation 4-10. So if you look at the ratio between D sub 84 and D sub 16, which are the percentile diameters, so the diameter for the 84th percentile and the diameter for the 16th percentile, if that ratio is less, oh, there's a table, okay. I forget about these things. If that number is less than 1.27, then you know your sediment is very well sorted, and that it's pretty reasonable to use a single size class. If you're in the range of 1.27 and 1.4, then I would suggest testing it. Okay, it probably is a good assumption, but there may be locally spots in your domain where it's not such a good assumption. Once you get to moderately well sorted, I would recommend using multiple grain sizes. For coastal areas, we rarely get into the range above 4. You know, even like 3 or 2. Most of the time, coastal sediments are moderately sorted or better. You know, I haven't seen cases where it's extremely poorly sorted or very poorly sorted. Okay, let me go back to where we were. Where were we? I think we were here, sediment characteristics. No, transport model, sediment transport formula, scaling factors, we talked about that. Hard bottom. Okay, the hard bottom is defined as any surface that is non-erodible. So, for example, the bedrock or a coastal structure that cannot erode. That is what we call a hard bottom. And Mitch talked a little bit about this last week, how you define it and where you specify it. If people would like, I can cover that again right now, but you know, Mitch did cover that last week. I see there's more questions. No. I think I'm not going to cover that. This part of the user manual is really self-explanatory and doesn't need any further discussion. Avalanching, Mitch did not talk about last week. It's basically the process of the sediment sliding when it reaches a critical angle of repose. So there's not many options for the user to change for this. You either turn it on or off. The default is actually off. I need to fix this. Let me highlight this here. The default is for highlighting to be off in CMS. Why? Because you rarely, for coastal, at least the problems that we do, you rarely reach the critical angle of 32 degrees. And so we just save time of not having to check for the critical bed slope every time step. If you have a case where you know you have steep bathymetry, then turn it on. Okay. In the case of the implicit solution scheme, there's an additional parameter, which is the maximum number of iterations per time step. When you use the explicit scheme, it doesn't have to iterate, it just applies it every time step. And then we talked about the two modes that you can run the sediment transport model in, as a single size model or multiple sized model. If you use a single size, only a single size, you specify the transport grain size, which is the material that you're moving, that you're transporting, and you can have a variable bed composition given only by the D50 data set. That's the only one you need for the hiding and exposure correction. And if you specify the card that says constant grain size, and what you're doing there is you're saying I only have one grain size and the bed composition is also equal to that grain size. So you don't have, it ignores basically the D50 data set. Okay. That's a way of turning off the hiding and exposure correction. And these cards are related to the boundary conditions. This sediment inflow loading factor is useful for cases where you have underloading or overloading. Let me give an example. Hawaii, areas where you have lots of coastal reefs. The reefs are basically a hard surface that don't have any sand on top of them, right? And so the transport capacity or potential in those areas is very small because it's limited by the availability of sediment. Okay, if you specify a boundary condition in an area that's limited by sediment, has a limited sediment supply, then you would want to reduce this loading factor, give it a smaller number. Okay, that's where you would want to apply that. Now, multiple grain sizes. It's already 2:30. I can't believe time went by so fast. Is there any questions before I go into multiple size sediment transport? I think we are going to stop for today because it is already 2:30 and today has been very, very busy. We covered a lot of material today and I think we can cover this tomorrow because we're not going to be able to finish in 30 minutes multiple size sediment transport anyway. Is that okay with everybody, or do people want to continue? I know I'm tired. Okay, so I think that we are going to stop here and continue tomorrow. Okay, well, I'll take questions. That's what I'll do. I'll take questions for today, and then we'll continue tomorrow on how to set up the multiple size sediment transport. Tudang has a question. How do you control your numerical instability when simulating sediment transport? That is a good question. One of the things you can do is you can reduce your scaling factors. Usually instabilities in sediment transport are because the bed change is occurring too fast. You can have spikes in the equilibrium sediment transport rates that cause lots of erosion, and then you have right next to that lots of deposition, and those produce instabilities in the model. One thing you can do is reduce the scaling factors. Another thing you can do is reduce the time step, or the hydro time step, but also the steering interval. When you take a big steering interval, that causes more errors in the wave height in the near shore. because we are predicting that water surface elevation for that wave model run. And that can lead to errors in the wave height in the near shore and can cause spikes in the sediment concentrations. Also, some formulas are more prone to instabilities than others. For example, we've seen that the Lunsert formulas tend to cause spikes in the near shore when you get really, really shallow, like less than 20 centimeters. Soulsby and Van Ryn tend to not do that as much. So there's several things you can do. You can try a different transport formula. You can reduce the scaling factors. You can reduce time step for hydro, which is the same for sediment in the case of the explicit scheme. You can reduce your steering interval. And also, you can check your bathymetry, right? Because if your initial bathymetry is noisy, that can cause instability problems. Those oscillations will grow if they're on the order of your grid size. And if you still have problems, then call me. There's more things. I talked a little bit about the bed slope coefficient, and that coefficient, that term is like a smoothing term, it's like a diffusion term. You can increase that bed slope coefficient, and that will smooth more your bathymetry and reduce instabilities. Usually, we don't have that problem with that. We don't have very often instability problems with sediment transport. Most of the time, it's hydrodynamics and due to very bad bathymetry or boundary conditions. Boundary conditions will produce instabilities if they're not well defined, if they're in the wrong place, if you have noise in your water surface elevation boundary, things like that. Tudang is asking a question, can you calculate the longshore sediment transport using multiple grain sizes? The answer is yes. You can do it with single grain size or multiple grain sizes. It's not a number that the model will spit out automatically. You have to post-process the results. The model will give you statistics of the sediment transport for your simulation time, and I'll talk more about those, the model statistics tomorrow or Friday. But once you have those data sets, you can place arcs in your domain and calculate fluxes across those arcs, and that will give you, for example, an average longshore sediment transport rate across that arc if you place the arc in the cross-shore direction. Sediment transport is, there's a lot of things you can do to post-process the results, and as I mentioned, it's really important to understand how we define the variables for when you compare with field data. I've seen people compare measurements of concentrations from an OBS directly to the model concentrations, and they're not the same, right? Because we use a depth average definition that it's weighted by the current velocity, and the OBS is only at certain points in the water column. Okay, so they're not directly comparable. Also, the OBS measurements are instantaneous, and our concentrations are wave averaged. So you need to be careful about comparing those things. What the parameters that we can use and we use frequently for calibrating the sediment transport are morphology change, and if you have estimates in literature for example, longshore sediment transport. You can compare model results to those values. But other than that, it's difficult. Is there any other questions on what I've covered today? Some of these things I'll talk more about tomorrow, about the how to process the sediment transport results, what kind of statistics you get from the model, how to specify the bed composition, I'll talk more about how to calibrate what parameters to look at first. So I'll stay on the line in case anybody has any additional questions, but feel free to email me or call us, any of us, if you have additional questions. I'll stay on the line for a few more minutes. Otherwise, feel free to leave the webinar, and I'll see you tomorrow.